Before I move on, is there any question about anything? All right, so just remember, kind of like what I was saying last week, chapter 5 is kind of like the hardest chapter because there's so many different formulas, and you kind of have to just look through all of these formulas and you kind of figure out like what are the key little things to help me differentiate this formula between the other formula. So you kind of pay attention to like the similarity between some questions, but also some of the difference some of the questions have. So what I'm going to do right now, I'm going to go ahead and just share my notes so that way we could continue on with chapter 5. And also just remember for the test correction, they're due on Wednesday. So if you are returning the test correction, if you see that you made a mistake on something in your test correction, you're always welcome to pretty much take that test correction down and just upload the new test correction. So if you do see there's something wrong with it, like I'm not going to grade it until Wednesday. So you have until Wednesday to do it. So please double check your answer and just make sure everything is good. All right. So if you remember, we left off with the conditional probability. So we left off with the conditional probability, and if you kind of remember, we were doing this for a two-way table, and we kind of realized, hey, for a two-way table, it's kind of harder to use this formula versus kind of using logic. So in the next couple of questions, what we're gonna do them, but in this one, it's actually advantageous to use a formula versus using a two-way table because we're not given the two-way table. All right, so if you look at this next problem, it says suppose that E and F are two events and that the probability of E and F is equal to 0.21 and the probability of E is equal to 0.4. Just remember 0.4 is 0.40 or 40%. Don't confuse it with 0.04 or with 4%. So you be careful with that. So it says, what is the probability that F given A or given E? So this is the given. So this is the given. So E is telling me this has already occurred, and I want to find the probability that if E already occurred, what's the probability that F occur? So for this one, we're going to say probability of F given E is equal to probability of E and F all divided by the probability of E. Everybody good so far with that notation? All right. And if you do have any question, just remember you can either put it in the chat or if you want, you can vocalize your question and I'll help you out. All right. So if you look at a probability of E and F is equal to 0.21. And you want to divide it by the probability of E, which is given to us at 0.4. But remember, that's 0.40. So you want to say 0.21 divided by 0.40. And you get 0.525. And we're done for this one. All right, so for this one, this is kind of just like the test model for that way you could kind of practice on this problem. The real type of question are going to come in the next several examples. But any question in regard to the first example? All right, so let's do this one. So it said the probability that it is Friday and that a student is absent is 0.03. Since there are 5 school days in a week, the probability that it is Friday is 0.2. What is the probability that a student is absent given that today is Friday? So for right now, we're just gonna ignore this portion. So we're gonna ignore what the problem is asking us, because first we wanna see what information is given to us. So if you look at the problem, there are two events that are given to us. What are the two events that are given to us? Sweet. So we have absent. That's definitely one of them. So absent, I'm gonna say is A, B. What's the other event that they're talking about? Perfect. Probably is Friday. So Friday. All right. So for absent, we're gonna put AB. If it's Friday, we're gonna put FR. All right. So let's look at the first sentence. So for the first sentence, it says the probability that it is Friday and the student is absent is 0.03. So right here, there's a keyword that the pretty much there's a keyword in this problem. What is the keyword, or what do you think is the keyword? It's not Friday or absent. Perfect. So we have and right here. So remember, the symbol for and is this one. So they tell us, oops, the probability is Friday and a student is absent. So what's the probability that it's Friday and a student is absent? Well, they tell us it's 0.03, so you put 0.03. All right. And that's what that first sentence gives us. So that's the information the first sentence is giving us. Cool, good job, Stephanie. Any question in regard to that first sentence? Okay, so let's look at the second sentence. So let me do this in neon green. So the second sentence says, since there are 5 school days in a week, the probability that it is Friday is 0.2. So in this part, did they mention anything about a student being absent? No. The only thing they mentioned the probability that it is Friday. So that's why we're gonna say probability is Friday is equal to 0.2. And if you're kind of wondering why is it 0.2, kind of think about it, there's only 5 days in the school week. So there's 5 days in the school and one of those school days is Friday. So you do 1 out of 5. Good, Emmy. And you get 0.20. So that's where the 0.20 is coming from. Is kind of figuring out there's 5 days out of the week, and of those 5 days out of the week, one of them is Friday. All right. Everybody go with that second probability? All right. So the last one, it said, what is the probability that a student is absent given that today is Friday? So right here, if I read this problem, what the keyword that tell me this is a conditional probability? Given, perfect. So what information is given to me? Like, do I know the student is absent or do I already know it's Friday? Cool. So it's given as Friday. So we're gonna write it probability. A student is absent given that, oops, is Friday. So this is information we already know. We already know it's Friday. So we want to see what is the likelihood that a student is absent. All right. So for this one, we're going to find the probability absent and Friday divided by probability is Friday. So if you look at both of these, let me put an arrow next to them. If you look at both of them, they're a little bit different. One of them, the Friday, is before, it says Friday and absent. The other one says absent and Friday. But you kind of know they're the same thing. Both of them are telling you the probability somebody is absent and is Friday. So it'll make no difference the notation for this one. So for this one, what's the probability they're absent and Friday? Well, no, I think you're jumping ahead. So with this probability over here, there you go, 0.03. All right. What's the probability is Friday? Yeah, 0.20. So if I do 0.03 divided by 0.20, you get 0.15, which is what Stephanie was giving me as the answer. All right, and we're done. So there's a 15% chance that a student will be absent given it's Friday. So you're telling us now that I know it's actually Friday, that percentage is actually going to go up because students are more likely to be absent on Friday versus any other day. So that's it for that first problem. Any question for the first problem, sorry? All right, let's do this other problem. So it said a math teacher gave her class 2 tests. 25% of the class passed both tests, and 72% of the class passed the first test. Given the student passed the first test, what is the probability they pass the second test? So right here, what are my two events? Or what's one of my events? You're looking ahead. We're in this problem right now, not the garage problem. All right, so we have pass first test. So we'll say this is PF, pass first test. Go, and pass the second test. So pass second. Go. All right, so those are my two events. So one of the event is a student passed the first test. The second event is the student passed the second test. All right, everybody good with those events? All right, so let's go ahead and now let's kind of distinguish what does the percentage tell me. So this one say 25% of the class passed both tests. So if it said 25% of the class passed both tests, what does that mean? Perfect. So mean the probability somebody passed the first test and the probability they passed the second test, that's equal to the probability of 0.25. So if you look right here, instead of saying and, we just said both, but essentially it means the same thing because we're saying we passed both exams. So that means we passed first exam and we passed the second exam. All right. Everybody gets so far with that first probability of 0.25. All right. So let's go on to the 72%. So the 72%, what does the 72% represent? So you want to be careful with that one, Amy. So if you look at it, it says 72% of the class passed the first test. So we want to say probably, oops, not a highlight, probably they passed the first test is equal to 0.72. Yeah, it's okay, Amy. All right. Everybody good on the probability of the first exam of passing the first exam is 0.72, and the probability of passing the first and the second exam is 0.25. All right. So let's look at the last sentence. So it said, given the student passed the first test, what are the probability they pass the second test? So right here, what are the keywords that tell me this is the conditional probability? Perfect. Good job, Stephanie. So it's the given. So given is automatically telling me this is the conditional probability. So what information is given to me? Is it given that they passed the first test, or is it given that they passed the second test? Perfect. So given that they passed the first test. So since that's the given, you put that after the vertical bar. So we want to find the probability they passed the second exam, given we already know they passed the first exam. You could kind of think about it. If you didn't pass the first exam, the chances that you pass the second exam is less likely. All right. Everybody good so far with my notation? Okay. So let's go ahead and write this as probability of P of S and P of F, all divided by the probability of P and F. So if you look at this, we already have each individual value. So we have 0.25, and you divide that by 0.72. Cool, good job, Lisa. So if I do 0.25 divided by 0.72, what I get? So you should get 0.347. And that's your final answer. So if you pass the first exam, so given that you pass the first exam, the probability you pass the second exam is 0.347. Cool. So if you look at it, that's higher than our and statement, and that makes sense because pretty much for the and statement, you're dealing with the entire population. But for right now, since we only care about students who actually pass the first exam, that's why the probability is actually higher, because we're looking at the people who pass the first exam. Well, they have a higher chance of passing the second exam given they already passed the first one. All right, and that's it for that second example. Everybody good for that second example? All right, so let's move on to this garage one. All right, so for this one, said real estate records show that 64% of homes for sale have a garage, 21% have a swimming pool, and 17% of homes have both feature. What is the probability that home has a pool given that it has a garage? All right, so for this one, what are my two events? So what are those two events that are kind of emphasizing? Cool, garage and pool, good job. So we got garage. So for garage, we'll set this as G. For pool, I'm actually gonna use PL instead of using P because it might get a little bit confusing because we already have P for probability. So if you put P, it might be a little bit confusing. Okay, so let's look at the 64%. What is the 64% for? Is that the probability they have a garage, the probability they have a pool, or the probability that they have both? Go garage. So say probability they have a garage is equal to 0.64. All right, what about the 21%? What does the 21% represent? Pool. All right, so the pool. You're good, Stephanie. All right, lastly, what does the 17 represent? Both. So both mean that's my answer. So that means the house should have a garage and a swimming pool. So we'll say probability of G and PL is equal to 0.17. Everybody good for the notation? So like for the type of problem, like the first thing you should do, you get everything and notate it. For that way, once you actually go to the question, it should be very easy to do. Because the question, like once you get to it, it shouldn't take you that long to answer it. But if you have everything like unorganized, it will take some time for you to do. So for this one, it says, what are the probability that a home has a pool given that it has a garage? All right, so hopefully by now you understand that given is the key word. So right here, what's given? Do I already know the home has a pool, or do I know a home has a garage? So I know the home has a garage. So we're gonna say probability, we have a pool, given it has a garage. So just remember anything that comes after the given, that's the information that should come after our vertical line. Everybody go with the notation? All right. So we're gonna say probability, you have a pool and a garage divided by the probability you have a garage. So if you look at the probability that you have a pool and a garage, well, that's 17%. And you divide that by the probability that you have, what do you call it, a garage, that's 0.64. So if I do 0.17 divided by 0.64, you get 0.266. Correct. So the question already said like the probability that the house have both of them. But for the question is saying like we already know it has a garage. So if we already know it has a garage, how likely is it that it has a pool? So the probability, so the 17% is saying like oops, sorry. If I don't know anything about this house, I should know that 17% have a garage and a pool. But what the given statement is saying, I already know that this house has a pool. So, well, sorry, I already know that the house has a garage. So if I already know the house has a garage, how likely is it that it has a pool? Which in fact, it make it more likely that it has a pool because if it has a garage, there's a more of a chance that it will have a pool. Versus if it doesn't have a garage, there's a less likely chance that it will have a pool. All right, but that's it. Ooh, that's it for that. Any question in regard to the last problem? All right. All right. So up next, we're gonna get into independent. So there's actually a way that we could check to see if two events are independent from each other. So technically, there's three different formulas, but we're only gonna kind of focus on one formula just to kind of make this easy. So for this one, we kind of have to go back to the definition of independent. So if you remember from last week, probably some of you don't remember last week, when we went over independent means that one event doesn't influence the chances of something else occurring. So if one event occur, the chances the other event will occur, it should still be the same no matter if one event occur or doesn't occur. Kind of the example I gave for that one, if I roll a die, and then if I roll, well, not roll, but if I toss a coin, the chances that the die will land on, say, 5 doesn't influence the probability that the coin will land on head or tail. So that's what independent is. So there's actually a formula to check to see if two events are independent from each other. So the formula that we're going to use, we're going to focus on the last one. And if you look at that formula, that's a formula for the multiplication rule, which makes sense because we said if we know the events are independent from each other, the probability of A and B should equal to the probability of A multiplied by the probability of B. So if I already know these two events are equal to each other, we're going to say they're independent. So if they're independent, they should be equal to each other. But if probability of A and B is not equal to the probability of A times the probability of B, we're going to say they're dependent events. So that's how we're going to mathematically show if two events are independent or if they're dependent. Everybody good with that before we go ahead and move on? All right, perfect.
Wait, can you say that again, please?
Cool.
Because yeah, I'm a little confused here.
Okay. So if you kind of remember going back to the multiplication rule, we said if I already know the events are independent, I could go ahead and just use this formula. Let me have a bunch of arrow pointing at it. We could just use that formula to find the probability of A and B occurring. But in this one, we're kind of going backward because before we knew the events are independent, and then we wanted to check to see, find the probability. So in this one, we actually have the probability, and we have to go based off the probability that we got. We want to check to see if they're independent. So if I do probability of A and B, if it's equal to probability of A times the probability of B, we say the two events are independent from each other. But if I do probability of A and B and it's not equal to the probability of A times the probability of B, then we say the events are dependent. So if they're independent, the two sides should be equal to each other. If it's dependent, then the left side and the right side are not equal to each other. All right.
Yeah, thank you, thank you.
All right, so let's go ahead and do our very first example. All right. So right here, I gave you probability of M, probability of N, and probability of R. So what we want to go ahead and see, if these events are independent from each other. So let's go to A. So A said if the probability of M and N is equal to 20% or 0.20, are the events M and N independent? So which two events do I want to check to see if they're independent? And just remember, you can either shout it out or just put it in the chat. Cool, perfect. So we want to check if M and N are independent from each other. So right now, we're only going to be using this. So we're going to say probability of M and N is equal to the probability of M multiplied by the probability of N. Cool. All right, so let's go ahead and check that out. So if you look at it, they already told us the probability of M and N is equal to 0.20. So we'll say 0.20 is equal to the probability of M. Probability of M, we already found it to be 0.8. Probability of N is equal to 0.25. So what's 0.80 times 0.25? Cool, thanks, Evan. So you get 0.20 is equal to 0.20. All right, so is the left side and the right side, are both of those sides equal to each other? Cool. So since the left side and the right side are both equal to each other, we say the events M and N are independent. And that's it. So that's how you check to see if both the events are independent based off of the probability that you get. All right. So let's go on to part B. So for part B, what are the two events that we're trying to see if they're independent? Cool, N and R. So we're gonna find the probability of N and R. That should be equal to the probability of N multiplied by the probability of R. So if you look at the already told the probability of N and R is equal to 0.3. So you put 0.3 over here. Probability of N is equal to 0.25. Probability of R, well, that's gonna be 0.6. Oops, sorry about that. So if I do 0.25 times 0.60, what would I get? So let's move that up here. So I get 0.3 is equal to 0.15. All right, is that a true statement? Is 0.30 equal to 0.15? No. So we put this saying they're not equal to each other. Since they're not equal to each other, we say the events N and R are dependent. Good job, Lisa. All right, and that's it for that one. Everybody go for the second part. All right, so let's go on to the next problem. So it says researchers survey 123 people about if they like pizza and they recorded their gender. The following two-way table displays the data for 123 people who responded. So the responded. All right. So if you look at it, we have male and female, and we have whether they like pizza or doesn't like pizza. So if you look at the very bottom, it says, are the events female and liking pizza independent from each other? So what we're trying to find out here, we're trying to find out did your gender influence the chances of you liking pizza? So do you think that like one gender like pizza more than the other gender, or do you think that they're pretty much the same? So if you think they're pretty much the same, you're thinking they're independent. If you think that gender has something to do with you liking pizza, then you're saying the two events are dependent from each other. So do you think that gender really doesn't matter whether you like pizza or not, or do you think it does matter? Cool. All right. So you think no, like it has nothing to do whether you like pizza or not. So what we're gonna do, we're gonna mathematically prove this. So for female, we're gonna use F for female. For liking pizza, well, we're gonna put LP for liking pizza. So what we have to do, we have to find the probability they're female and like pizza. And this should equal to the probability they're female times the probability they like pizza. All right. Everybody good so far with this? All right, so let's go ahead and substitute it. So let's go ahead and find this. So we want to find how many total female like pizza. So how many females do we have that like pizza? Cool, good job, Lisa. So if you look at, if you select like pizza and who are female, if you look at what get overlap, 60 get overlap. So you want to put 60 divided by 123. All right. So for the next question, it says probability of female. So how many total female do I have? Oh, good job. They get 90 out of 123. How many people do we have that like pizza? Good job, Lisa. They get 82, and you too, Lauren. All right, so what we want to do, we want to kind of check to see if the left side equal to the right side. So I'm going to first do 60 divided by 123. So 60 divided by 123, you get 0.4878. Now let's do the right side. So for the right side, we do 90 divided by 123, and then we multiply by 82 divided by 123. When you do that, what do you get for your probability for the right side? Yeah. All right, so if you look at the left side, the right side matches up. Since the left side and the right side matches up, that's kind of telling you that the two events are independent. So we're going to conclude they're independent. So what that mean is saying gender has nothing to do whether you'll like pizza or not, because both female and male like pizza at the same percentage. All right. And that's it for that first problem. Any question in regard to that first problem? Well, in our thing, it does have to be exactly the same, because if you look at both percentages are exactly the same. But using the real world, you'll hardly get that both of them are the same. So they're slightly, if they're slightly the same, we say yes, they are independent. But like for test question and quiz question, I will always make it, if they are independent, that they're always equal to each other. All right. Any other questions? Sweet. All right. So let's practice with one more, and then we'll move on to better things. So for this one, say researchers survey recent graduate of two different universities about their annual income. The following two-way table displays the data for the 300 graduates who responded to the survey. So we have people who went to University A and University B, and we have their annual income. So we have under 20,000, 20,000 to 39,999, and 40,000 and over. So if you look at the question, it said, are the event income is 40,000 and over, and attending University B, are these two events independent? So we kind of want to see if the university that you go to, is that influence your pretty much your annual income. So if they're independent, I mean like the university have nothing to do with your annual income. If they're dependent, I mean that depending on which university you go to, you're more likely to make more money. All right. Any questions so far? All right, so let's go ahead and find this. So for this one, income is 40,000. Where you gonna put 40,000 plus? And for your attended University B, well, that's easy. Where you put B. So what we have to do, we have to find the probability somebody make 40,000 plus and went to University B, and that should equal to somebody who make 40,000 plus multiplied by the probability somebody went to University B. So remember, if they're independent, that means they should equal to each other. If they're dependent, that means the left side and the right side will not equal to each other. So how many people do we have that make 40,000 and more and went to University B? Good. So that should be 40 out of 300. And if you're having a hard time kind of figuring that out, here go the 40,000 and over. Here go people who went to University B. If you look at where do they overlap, well, they overlap at 40. So that's why we choose 40. Yeah. How many people do we have that made 40,000 and over? Just 75. Lastly, how many people do we have that went to University B? Oh. All right, so any questions so far on how I got any of those three fractions? Okay, so let me go ahead and work that out. So we do 40 divided by 300. All right, that's 0.133, and that 3 you continue on. Then we'll do 75 divided by 300, multiply by 120 divided by 300. You get 0.10. All right, so is the left side equal to the right side? Well, thanks, Lisa. No, so we'll put no. So we'll say the event, oops. All right, so we'll put the event of income is over 40 and over, and attending University B are dependent event. So that means it does depend, because saying like one university, if you go to one university, you'll earn more annual income compared to if you attend another university, you might not pretty much get as much for your annual income. But that's it for that last problem. Any question in regard to this last problem? All right. So if you look at this problem, like the key thing for this one, they're asking me, are these event independent? So in a test or in a quiz, if I ever ask you, are these two events independent from each other? What I want you to do, I want you to pretty much mathematically prove to me, are these two events independent from each other? All right. Any question in regard to the last problem before we move on to something new? All right, so let's move on to something new. All right, so up next, we're gonna go ahead and do something that we already did before, but what we're gonna do, we're gonna add like an extra twist to it. So before, we were doing a multiplication rule where we're saying probability of A and B is equal to probability of A multiplied by the probability of B. All right. So that's what we're doing, and we're doing this last week. So we're using the multiplication rule. So if you remember, we use the multiplication rule when we have independent event. So, and remember, independent event just means that the event, one event, shouldn't influence the probability of the other event. But what if one event does influence the probability of the next event occurring? So that's what we get to this portion right here, which is saying without replacement. So without replacement meaning once I make that selection, I can't make that selection anymore because pretty much we're not putting it back into the table, we're not putting it back into the population. So without replacement meaning once I pick that object or that person, I can't reselect that person or that object because I already selected it. So once it's selected, you can't reselect that object again. So anytime in a test or quiz, if you see without replacement just meaning once you select it, you can't reselect that object. So since we can't reselect that object, that make this event a dependent event. So that's why we're gonna use this formula. So if I want to find the probability of A and B, all I have to do is get the probability of A, and I have to multiply by the probability of B, given A has already occurred. So to kind of enlighten you why we have that formula, because if you remember for the and statement means we're making multiple selection. So right here saying we select A first. So that way right here for the given is already saying A has already happened. So it's saying find the probability of B occurring given A has already occurred. So we're going to use this formula in order to find the probability of A and B. Like right now, it might seem a little bit difficult, but once we actually do the problem, hopefully it should become a little bit easier. So let's do this first problem. So it says 2 marbles are drawn without replacement from an urn containing 4 red marble, 5 yellow marble, and 2 blue marble. Determine the probability that. So before we get started with that, let me draw this out for you. So we have our urn. So if you look at it, it said we have 4 red marble. So we'll say 1, 2, 3, 4. We have 5 yellow marble. So we have 1. Hopefully you can see that. 2, 3, 4, 5. And lastly, if you look at that, we have 2 blue marble. Cool. All right. So if you look at part A, we want to find, or so before this, we go with part A, part B, or part C. Let's see why is this multiplication rule and why is this a dependent data set. So how do I know this is, we're supposed to use the multiplication rule? What's like one key thing that they tell us that we should automatically know this is the multiplication rule?
Without replacement?
Not that it's telling us without replacement, but before that, what do they tell us? You're close.
2 marbles are drawn?
2 marbles are drawn. Can remember, whenever we're making multiple selection, that's how we know we're going to be doing the multiplication rule. So the key thing is that they tell us 2 marbles are drawn. This is what tells us we're doing the multiplication rule. What is it that tell me that this is a dependent data set? And somebody already said this before. Without replacement, good. So this is what tell me is dependent. So we know the multiplication rule because they say we're making more than one selection. We're doing 2 selection. We know this is dependent because it tells us it's without replacement. All right. Everybody good for that so far? All right. So if you look at it, so part A say both are red. So that means I want both of my selection to be a red marble. So that means we want the first one to be red and we want the second one to be red. Cool. All right. So which color should the first one be? Cool. Very good. We got that one right. So we know the first one should be red, correct? So this means I'm going to randomly select the marble. I'm going to take it out. So I already know I selected a red marble. So once I say I selected the red marble for the first one, I pretty much have to take that I already selected a red marble. So which color do I want the second marble to be? Red. And then in this back end, what marble? So in the front, you want to put like which marble you want. And then after the vertical line, you put which marble was already selected. So you put that this is R. All right. Everybody good so far with my language or with the notation? All right. So what's the probability that the first marble is red? Oh, good job, Javier. Oops. 4 out of 11. So remember, for the second one I already told you the first marble was already red. So if the first marble was already red, what's the probability that the second marble was red? So yeah, so you have to be careful. So remember, once I already take one marble out, I have one less marble. So since I have the one less marble, you have to do 3 out of 10. Everybody got, I got 4 divided by 11 times 3 divided by 10. Okay, so let me work that out and we'll find ourselves a good answer. So you roughly get 0.109. And that's your final answer for A. So kind of look at the difference between multiplication rule with replacement or independent and multiplication rule without replacement, which is dependent. So like the probability are not going to be drastically off, but they will be off if you use the wrong formula. All right, everybody good for A. All right, so let me put back this marble and let's do B. So if you look at B, we want the first marble drawn is red and the second is blue. So we want the probability the first one is red and the second one is blue. So we're gonna put two things multiplied times each other. So what should I put for my first probability? What's the first marble I wanna get? Cool. So it should be red. Good job, everybody. All right. So the first one should be red. What do I want the second marble to be? Cool. So I want it to be blue, but what had already happened when I selected the first marble? The first marble we said was what? Was red. So we say probably the first one or the second one is blue given the first one was red. Everybody kind of go with that? Okay. So what's the probability the first marble is red? 4 over 11. So here, let's take away this red marble now. So now we have one less marble. So what's the probability that the second marble will be blue? Good, 2 out of 10. So if you do 4 divided by 11 times 2 divided by 10, you get 0.07, and what do you say? That's a 3. All right, and that's it for B. Any question for B? All right, let's do C. So the C said the first marble drawn is blue and the second is red. So if you look at the difference between B and C, all that's happening, we're switching the order. So instead of saying we get red first and then blue, now we're saying we're gonna get blue first, then we get a red marble. So what's the probability that the first marble I choose is blue? 2 out of 11. What's the probability that the second marble I choose is red? So if you work that out, you actually get 0.073. And that's it for C. So if you look at it, it doesn't matter the order. So if I say red, then blue, or blue, then red, it's the same probability because you're still at the end of the day getting a red marble and a blue marble. Everybody go for the C. All right. All right, so let's do these next one. So it said 2 card will be selected without replacement from a standard 52 card deck. So if you don't know about 52 card deck, if you go all the way to the bottom of the notes, I essentially have all of the 52 cards there, so that way you can learn about them. So these are spades, these are clovers, these are hearts, and lastly, these are diamonds. So if you don't know anything about cards, you might want to stay in this page and work out the next problem. Because you do kind of want to know something about cars. So one thing you have to just know about cars, there are 52 cars. And if you look at it, there are going to be 26 black cars. And there are going to be 26 red cars. Essentially, half of the deck is black, half of the deck is red. So let's go and see if I can find that problem again. There we go. All right. So if you look at the thing, it says 2 card will be selected. So this is very important that they tell me 2 card will be selected because the 2 cards are telling me this is the multiplication rule. And then if you look right here, tell me without replacement, and now telling me they're dependent event. So that's how I know we're doing the multiplication rule, and it has to be for dependent event because they tell me 2 cards are selected, and because they tell me it's without replacement. So for part A, it says find the probability the first card is a heart, and the second card is a spade. All right. So let's do this. So the first card has to be a heart. So we'll do a heart right there. The second card has to be a spade. So that's an upside down heart. All right. So far, everybody good with my notation? Right here, let's just write it out. So for this one, which suit do I want the first card to be? Do I want the first card to be a heart, or do I want the first card to be a spade? So we want the first card to be a heart. Perfect. What about, oh nice, I didn't know you could do a heart like that on the chat. Good job, Raimundo. All right, so what about for the second card? The second card, we want it to be which suit? All right. So we want it to be a spade. But for this one, which information do we already know? Raimundo's on a row. So for this one, which information do I already know about the first card? The first card has to be, there you go, it has to be a heart. All right, so what we want to do, we want to find the probability the first card is a heart, and then we want to find the probability the second one is a spade given its heart. All right, so let's go down here. So if you look right here, here are my spades. So how many spades do I have? So if I look right here, I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. So you get 13. So let's go back up here. So we get 13, and you have a total of 52 cards. So we'll put 13 out of 52. So let's focus on this one now. So we want to find the second one, which is probably a spade given the first one is, oops, sorry, they're the same thing. So yeah, so first one, the probability of heart, I accidentally said spade, but it was supposed to be heart. So the probability of the heart is 13 out of 52. So say the first card I picked was this heart right here. So I picked the Jack of Hearts. So if I pick a Jack of Hearts, how many cards do I have that are left over? 51. But did that affect how many spades I have? No, because I still have 13 spades. So when I do this, we'll say 13, but out of 51 cards. So if I do 13 divided by 52 times 13 divided by 51, this will equal to 0.064. And that's it for A. Any question in regard to A? So let's do B. So for B, it says, well, the condition for this one is telling us that the first card has to be a heart. Okay, if you look right here, we said the first card is a heart. So that's reflected over here. So since we're saying the first card has to be a heart, that means that the first card we drew was a heart. And now we want to know that the second card is a spade. So for this one, doesn't really affect your probability that much, just that you have one less. And also the same without replacement. So once I select the heart, that means I can't reselect that heart again. All right, so let's do B. So it says find the probability the first card is a 10 and the second card is a king. So I want the first one to be a 10, and then I want the second one to be a king. So that means we want to find the first one is a 10, and we want to multiply that by the probability the second card is a king. But remember, the first card was already a 10. So we have to say probably 10 times the probability we have king given the first card was a 10. So let's go back to that chart and let's see how many 10s do I have. Oh, good job, Stephanie. You got it. All right. So if you look at it, I have 1 10, 2 10, 3 10s, 4 10s. So you have 4 10s. So I have 4 10s out of 52. So if you look at it now, we want to find the probability we get a king given the first one was a 10. So seeing that the first one was a 10 really doesn't affect us. So we're going to look and see how many kings do we have. So say by chance we selected the 10 of spades. That doesn't affect us from getting a king of spades, a king of clover, a king of hearts, or a king of diamond. So we still have 4 kings. Like if I always say the first card of the king, the second card of the king, now that will affect it. So you get 4 out of 51. So you put the 51 because there's 1 card less. So you get 0.006, and that's it for that one. Okay. Any question for that last problem? All right, so let's do this next example. It says a table of 5 students have 5 senior, 2 junior. The teacher is going to pick 2 students at random from this group to present homework solution. Find the probability that both students selected are junior. All right, so how many total students do I have? So 5 total students. How many students am I selecting? 2 selection. All right, and for this one, we're gonna assume that once a student present, well, they can't present again. So once we get one student to present a problem, we're not gonna make that student present again. So we want both of the people who present, both of them to be juniors. All right. So what's the probability that the first person who present is a junior? Oh, so you say, well, let's check that again. There you go. 2 out of 5. So if I selected the first person to be to present, and if that person was a junior, now instead of having 2 junior, now you only have 1 junior left. So what's the probability that the second person to present is a junior? 1 out of 4. Good job. So if I do 2 divided by 5 times 1 divided by 4, you get 0.10. So you get a 10% chance that the 2 people that are selected from that table, that both of them are juniors. All right, and that's it for that last one. All right, everybody go for that last one. All right, so let's do this next one, then we're gonna move on to something else. It says, in a shipping of 20 computers, 5 are defective. 2 computers are randomly selected and tested. What are the probability that both are defective if the first and the second one are not replaced after being tested? All right, so for this one, how many computers do we have in total? Good, so total. How many computers are being checked, or how many of them are being tested? So let's say 2 computers are being So since I know 2 computers are being tested, this is pretty much telling me I want to do the multiplication rule. And then if you look at it, does it make sense if I test 1 computer to see if it's defective does it make sense for me to retest that computer to see if that computer is once again defective? No, because like once you check that computer, if it's defective, you kind of want to move on to the next computer. So if you kind of look at this one, we're doing the testing without replacement. So once I check that computer, that means I can't check that computer a second or third or fourth time. Like you set it aside and you check a new computer. So that will make this without replacement. All right, so let's find this. Cool. So if you look at the problem, we want to find the probability that both of them are defective. So we want to know the probability the first one is defective and the second one is defective. So for this one, if you want to write it out, you can write it out as this. Probably the first one is defective times the probability the second one is defective, given the first one was already defective. So we want to find the probability that both of these computers are defective. So what's the probability that the first one is defective? 5 out of 20, perfect. What's the probability the second computer is defective? 4 out of 19, good job. But you have to realize if the first computer was defective, that means you have one less computer to check, but also you have one less defective computer to check. So we say 5 divided by 20 times 4 divided by 19. And that will give you 0.05, and we'll round that up to 3. Good job. All right, and that's it for that one. So this is how you do it when you have dependent data set, but you want to use the multiplication rule. So if you have dependent data set, you have to just remember you have one less to choose from, and that's your second selection. Any question for this one before we move on? All right. So we're on to the last thing for 5.5. So for 5.5, we're gonna get into something called counting technique. So the counting technique is telling us like how many different ways can we do a certain sequence or a certain arrangement. So for this one, we're gonna learn 3 different counting techniques. So the first counting technique is the multiplication counting technique or counting rule. Let's put counting rule. So for this one, all you have to do is you have to look at what are all of the events occurring and how many different ways can those events occur, or how many different ways can those, well, let's say events occur. So depending on how many different ways can those events occur, that's what your P, your Q, and your R are gonna be. So the P, the Q, and the R are gonna represent all of the different ways that these events could occur. And then what we're gonna do, we're gonna multiply them all out, and that's gonna give us a total amount of outcome. So for this problem, we're actually gonna do it the long way, and then I'm gonna show you how to do it with the multiplication rule. For that way, you can kind of see how is the multiplication rule working. All right. So for this next problem, it said the local pizzeria offer a choice of 2 pizzas, supreme or vegetarian, 3 sides of chip, 3 side chip, salad or coleslaw, and 4 drink, juice, Coke, ginger, beer, or water. Oh, actually, this one should be this one should be 5 because there are 5 different drinks. Oh no, wait, no, it should be 4. I put ginger and beer separate. So yeah, so you have juice, you have Coke, you have ginger, and then ginger beer, and then you have water. So for this one, said for dinner, I decided to have 1 pizza, 1 side, and 1 drink. How many possible meals do I have to choose from? So when I first order, what are my options for my pizza? So I have two options. So I can either choose Supreme or I could choose vegetarian. So those are my two options. So let's move away from our pizza. So once I choose which pizza I want, so I can either choose Supreme or I could choose vegetarian. Then I could choose 3 sides. What are the 3 sides I could choose? Cool. So chip, coleslaw, and salad. So you see chip, salad, or coleslaw. Chip, salad, or coleslaw. So those are all. So once I choose my pizza, so say if I choose the Supreme, now I have 3 options. So I can either choose chips, salad, or coleslaw. But that's not it. Because now what we could do, now we could choose a drink. So how many different drinks can I choose from? So we could choose from 4. So this might get a little bit messy. So when we choose our 4, we can either choose a juice, a Coke, a ginger beer, or water. But the thing is, if I pick a salad, I could also make those 4 selections. I could select a juice, a Coke, ginger beer, or water. But if I pick coleslaw, I can also make those 4 selections. So we could say juice, Coke, ginger beer, or water. But if you look at, what about if I choose a vegetarian pizza? If I choose a vegetarian pizza, at the end, I also have to select a certain type of drink. So I also have, we also have those 4 options right here. That we have juice, Coke, ginger beer, and water. Let's extend this one out because I don't have enough space anymore. We have juice, Coke, ginger beer, and water. And lastly, we'll do this one too. We have juice, Coke, ginger beer, and water. So technically, those are all of the different combination I could get. So if I wanted to, I could get a Supreme pizza. I could pick chips, and I could get a juice. So that's one of the many different orders I could get. Or if I wanted to, I could get a Supreme pizza, get some chips, and now I could pick Coke. And this will be a totally new combination because it's different because instead of choosing juice, we're choosing Coke. So if you look at this one, how many different combination of this order can I have? You're sure about 12? Well, if you look right here we have 1, 2, 3, 4. Then you go 5, 6, 7, 8. Then you go 9, 10, 11, 12. Then you go 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. So we had 24, not 25. So we had 24 different orders that we could possibly order. So we could order like a vegetarian pizza, get a salad, and get Coke. Okay. Yeah, sorry, no. For the whole order for vegetarian and Supreme. So that's the way they could do it if you're using a tree diagram. But the thing is, with a tree diagram, it get a lot confusing pretty fast, especially if you have a lot of order or a lot of different combinations. So that's why you kind of want to use the multiplication rule. So for the multiplication rule, you kind of have to look at, okay, for the combo, what does it have? Like, what are the things that you could choose in this combo? Like when I first get started with the combo, so good. So we could choose a pizza. You could pick the size. And you can pick the drinks. So what I want you to put, I want you to just say, how many options do we have for each one of them? So when I'm choosing the pizza, how many options do I have for the pizza? What about for the sides? How many options do I have for the sides? What about for the drinks? Oh, then you multiply all of them out. If you multiply all of them out, what do you get? 24. And that's the 24 we originally started off with. And that's it. So that's how you want to check to see how many different outcomes you could get. All you have to do is see like, okay, first, what are all of the events? The events are you're getting a pizza, you're getting side, and you're getting drinks. And then you see how many options do you have for each one of those events. So for pizza, I have 2 events. Sides, I have 3 events. Drinks, I have 4 events. If I do 2 times 3 times 4, you do 24. That will be, well, so you're saying we're choosing 2 sides? So if we're doing 2 sides, we go pizza. That's actually a good question. You go sides, and then you go sides again. And then you go drinks. But question, can I pick the same size or do they have to be different size? Like, can I pick chip twice? All right. All right, so we were gonna say different. So for this one, how many options do I have for pizza? How many options do I have for sides? Or for the first side? What about for the second side? How many options do I have? 2, perfect. What about for drinks? 4. So now if you multiply all of that out, you should get, I think, 48, if math is correct. Should be 48. What about if I could pick the same sides? So say I could pick chip twice. So you could pick 2 pizza. Right here will be 3 sides. So what should I put right here? Good, 3. And here, let me do that one. 2 times 9 times 4. Yeah. So you get 72. That's actually a really good question. All right. And that's it for that problem that we just made up right now. So yeah, so if we're picking 2 sides, you put size twice. And then you say, if we're doing it without replacement means pretty much once you select that object or once you select that side, that means you can't select it again. So that's the red line. But if you can select the same size twice, that's the blue line. All right. Everybody go for that. Well, technically second and third question. All right, let's do this next question. So it says there are 5 shirts, 3 pants, 4, no, thank you for that question. 4 shoes and 2 belts. Ryan can use to make a suit. How many possible suit combination can he do? So kind of think about it. If you're going on a trip and you're trying to figure out how many different outfits can you do, and we're gonna just assume if I change one part of the outfit, it's a completely new outfit. So if I change the belt, we get a brand new outfit. So how many different ways can I change my suit? All right, you already gave me the answer. Well, we have shirts, we have pants, we have shoes, and we have belts. So if you look at it, there's 5 shirts, there are 3 pants, there are 4 shoes, and there are 2 belts. So if you go ahead and multiply all of these, I presume everybody is correct on the chat, and we're gonna say there's 120 different ways. And that's it for that problem. Any question in regard to the last problem? All right. So let's do the next 2 problems, and then we're gonna move on to a different counting technique. So it said there are 4 ways from Los Angeles to Dallas. There are 3 ways from Dallas to Green Bay. How many possible ways will John have to get from Los Angeles to Green Bay? So right here, we're assuming that there's no time conflict. So these 4 flights that fly into Dallas, that means they could get the 3 other flights that go from Dallas to Green Bay. So we're gonna assume there is no time conflict. So for this one, how would I do this one? So say LA to Dallas. Ooh, not that large. And then we could say Dallas to Green Bay. Cool. All right, so if you look from LA to Dallas, there's 4 different flights that will take me from Dallas, well, sorry, from LA to Dallas. And then if you look from Dallas to Green Bay, there's 3 different flights that will take me there. So if we do 4 times 3, you get 12. So there's 12 different flight combinations that we could use that will get me from LA all the way to Green Bay, Wisconsin. All right, and that's it for that last example. Any question for that last example? All right, so let's do this last example before we go on to the combination, or sorry, permutation. All right, so this one says calculate how many 5-digit password for a cell phone can be formed from 0 to 9 where no digit can repeat. All right, so let's first find that one. So we have this cell phone, and kind of if you, well, if you have a cell phone, you know, in order to go into the cell phone, or if you're not using the face recognition, stuff like that, or your finger recognition, we need 5 digits for that way we can make a 5-digit password. So what we have these 5 digits. So we have the first digit, we have the second digit, we have the third digit, we have the 4th digit, and the 5th digit. So those are the 5 digits that we're coming up with because we want to come up with a password. So they tell us we could select any number from 0 to 9. So if I could select any number from 0 to 9, how many options do I have? Cool, 10. So we have 10 options. Cool. Okay, if you can't think about it, you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 10 options. All right. So if you look at the last thing, it says where no digit can be repeated. So it's pretty much telling us we're doing this without replacement, because saying once I choose this number, I can't choose this number again to be part of my password. So say if I choose 5, that means I can't choose 5 anymore because I already chose it, and it's saying we're doing it without repetition. All right. So when I'm choosing the first number, how many options do I have to choose from? What about when I'm choosing the second number? How many options do I have to choose from? Cool, thanks, Javier. So you get 10, 9, 8, 7, and 6. So let's do 10 times 9 times 8 times 7 times 6. Oop. So there's technically 30,240 different passwords I could choose from if none of the 5 number can repeat. All right, everybody go with a 30,240. All right, so for this one, it's saying, what is the probability a random person can guess the correct password for a cell phone? So if we, sure, which part do you want me to do again? This part right here, Alejandro? Or, all right. So if you look at it, we could choose a number from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So I could choose any of those 10 numbers. So when I'm first choosing for the first digit, I could choose any of these 10 numbers. So that's why for this one, I have a 10. So say the first number for my cell phone is 5. So I choose 5. So that means I can't choose 5 anymore. So now when I'm choosing the second number, now we only have 1, 2, 3, 4, 5, 6, 7, 8, 9 numbers. So say I choose for my second number, let's say I choose 8. So that's my second digit. So that means I can't use 8 anymore. So that means I have 1, 2, 3, 4, 5, 6, 7, 8 numbers I could choose now from. So say for my third number, I choose 6. So now I can't use 6 anymore when I'm choosing the 4, so I only have 7 options. So say I choose 3 now I only have 6 options. So that's how I get the 10 times 9 times 8 times 7 times 6, because essentially every time I'm picking the next number, since I can't repeat the number, I'm losing one of the options. All right, and that's it for that part of the question. So technically, there's 30,240 passwords that you could use for your cell phone if it has 5 digits. All right, everybody good on the 30,240? All right, so for the second question, or the second part of the question, it says, what is the probability a random person can guess the correct password for a cell phone? So we want to find the probability to get it correct. So if you want to find the probability that somebody could guess correct your password, well, how many correct passwords are there out of the 30,240 passwords? There's only one. They say 1 divided by 30,240. Let's see what that gives us. 1 divided by 30,240. So if you do it on your calculator, you get 3.3 e negative 5. But remember, the e to the negative 5 means you get the decimal place and you move 5 spaces over to the left. Then you get 3.3 and you go 1, 2, 3, 4, 5. Then you go 0, 0, 0, 0. And that's it. And that's it for that last problem. Any question for that last problem? All right, so this is a counting technique. So up next, we're again to something called permutation. So for permutation, it has a few rules. So let's get to these rules. So for permutation, also you're gonna need your TI-83 or 84 calculator, because we're gonna do this with the TI-83, 84. So that way it will go much easier. All right, so if you look at the rule, it says the n objects are distinct. So that means each object that we select, we can't have any repetition. So all objects should be distinct, so they should be different. So second one, it says repetition of object is not allowed. So that means we're doing it without replacement. So once I select an object, I can't select that object again. So that wouldn't mean repetition of object is not allowed. It is telling us we have to do it without replacement. So once you select it, you can't select it again. Lastly, order is important. So for permutation, the way I organize the data set make a big difference. So say if I have a data set and I have A, B, C, if I rearrange it to C, B, A, these are different from each other. So for this one, order is important. So A, B, C will be different from you getting C, B, A. Everybody kind of good with that? Okay. So for permutation, you're gonna have two letters. It's gonna be N and R. N is how many options do you have? So we're gonna say total option. R gonna represent how many are you choosing. So of the total option, we want to see how many do we choose. So how many option so when I say n is how many total option, r represent how many option are we selecting. So I might have 20 options, but I only care about the 5 options. All right, everybody good with n and r? All right, so let's do this one. So for this one, said n is equal to 7 and r is equal to 4. And I'm already telling you this is permutation. So we're going to say 7 P 4. So this is what I'm going to enter into my calculator. So I actually should have a calculator right here. So what I want you to do, I first want you to enter the n. So for this one, what was my n value? So enter 7. Next thing I want you to do, I want you to hit right here where it says math. If you look at it, I kind of over it with my cursor. So I want you to go right here where it says math. So hit math. And then if you look right here, it says PRB on the top right hand corner. So go where it says PRB. And if you look at the first option, it says random. If you look at the second option, it says NPR. You're gonna want to use NPR. So you select NPR. Any question on how to select NPR? Lastly, what you want to do, you want to enter your R value. In this case scenario, what was my R value equal to? 4. So you enter 4, you press enter, and we're done. So for this one, I'm telling you, if I have 7 objects and I want to arrange these 7 objects, but I only want to arrange the 4 objects of the 7, there's a 840 different way that I could get 4 of these objects and arrange them. And that's it. Any question on how I got the 840 using the calculator? Wait. Go to notes. So you get 840. Yeah, for this one, we're only gonna focus on the calculator. I'm not gonna ask you to do it by hand, so you don't have to worry about doing the formula. You just use a calculator for this one. All right, so let's get to the next one. So it says, in a race in which 6 automobiles are entered and there are no tie, in how many ways can the first 4 finisher come in? So for this one, oh, perfect, Stephanie. So for this one, what you have to realize, for this one, we have 6 automobile racing. Are all 6 automobile racing, are they different from each other, or are they all the same automobile? Cool, so they're all different from each other. So for this one, also, if you look at it, for this one, the order matter. So since they're racing and we want the first 4 finisher, does the order matter? Like, does it matter who come in first, second, third, fourth, or are they all the same place? Yeah, so the order does matter. So that's why this is permutation. So what's my n? How many objects or how many automobiles do I have to choose from? 6. How many total automobile am I choosing? So we're gonna do 6p4. So let me do that in my calculator. So we do 6 math PRB, we do NPR, we do 4, and we get 360. So there's 360 different ways that the first 4 finisher could come in if there's a total of 6 automobile. So that's what the 360 is telling us. It's telling us, hey, there's 360 different ways that these first 4 cars could come in, given that we have 6 automobile racing. All right. And that's it for that second one. Any question for that second problem? All right, let's do this third and the fourth one. So it says a corporation had 10 members on a board of directors. In how many ways can it elect a president, vice president, secretary, and treasurer? So for this one, are all the board members the same, or can we assume they're all different? Cool, so they're all different. So for this one, does the order matter? Does it matter who I place as president, vice president, secretary, and treasurer? Or are all of these positions the same position? Cool, so the order matters. So this will make it permutation. So what's my n? How many people do I have to select from? How many people am I selecting? Cool, good. And the reason we're selecting 4 is because we're selecting somebody to be president, vice president, secretary, and treasurer. That's why R is equal to 4, because we have 4 positions to fill. So lastly, we'll do 10p4. So somebody already did this for me, so it'll be 5,040. All right, and that's it for that one. Any question for that last one? All right. I think this should be the last one. Correct. All right. So this should be the last one for permutation. So for this one said, if we have 4 people waiting in line to pay as Sprout, in how many ways can we arrange Archer, Ben, John, and Rick in a queue? So kind of think about it, they're all waiting in line, and we want to find out the different way that we could arrange them. So for this one, are all 4 people different? Perfect. The way that I arrange them, does it make a difference, or are all of them the same? So why are they all different? Yeah, because essentially you have somebody who's first in line, second in line, third in line, or fourth in line. So it's drastically different. So for this one, I'm going to do a little bit different. So that way you can kind of see where the permutation rule is coming from. So say here is the line. So here's the first person to pay out, second person to pay out, third person to pay out, and the fourth person to pay out. So say we have these people right here. If I wanted to choose one of them to go here, how many people do I have to choose from? 4. So say I decide to put Archer here. So Archer goes right here. Now I want to fill out this third position. How many people could go in that third position? 3. So say John is in this third position. How many people could go now on the second position? 2. So say I pick Rick over here. So then if I want to pick how many people go in the first position, there's only 1. So if you do 4 times 3 times 2 times 1, what do you get? Yeah, you get 24. And if you do that with your calculator, you do 4 math, PRB, MPR 4, you get the same answer. So that's where the permutation rule is getting it from. It is saying you have one less option to fill, and that's why the order matter for that one. All right, but that's it for permutation. Everybody good for permutation? All right, so we're gonna do combination. Combination is gonna be the last thing we do for today. So for combination, this rule and this rule is exactly the same thing for permutation. Both of them say that each object should be distinct from each other, and we can't choose the same object more than once. So that's what the first two rules are saying. It's the same thing as the permutation. The one thing that makes combination and permutation different, for combination, the order is not important. So the way I arrange the data set, it doesn't matter. So if I do A, B, C, or C, B, A, both of them are exactly the same thing for combination, because in combination, the way I arrange the letter doesn't matter. If I get A, B, C, this is one combination because we're just looking at the letters. All right. Everybody good so far with that? All right, so let's do this first problem. So if you look at this first problem, I already gave you the N, I already gave you the R. So this one we're gonna do 7C4. So if you kind of imagine P for the last one represented permutation, if you look at this one, C represent combination. So if I go right here, we do 7, math, PRB. But if you look right now, right below NPR, you see NCR. So you want to use NCR. And for this one, you want to choose, I think it was 4, and you get 35. So you get 35. And that's your final answer for that first problem. Any question for that first problem? All right, so let's do the second problem. So for this one says example, an election ballot asks voter to select 3 city commissioner from a group of 6 candidates. In how many ways can this be done? All right, so for this one, can we assume that all 6 of these candidates are different from each other? Cool. All right, for this one, is repetition allowed? So can I choose the same person to be the 3 city commissioner, or do each one of those city commissioner have to be different? Yeah, it should be no, they should all be different. So for this one, repetition is not allowed. But for this one, does it really matter who I pick first to be city commissioner or second to be city commissioner, or third to be city commissioner, or are they all the same? Well, for this one, it should be all the same because remember, it doesn't matter who I pick first, second, or third, because at the end of the day, they're all just going to be city commissioner. So for this one, what you have to decide, how many people do we have to choose from? So what is my N? Cool, 6. All right, what is my R value? 3. So we do 6 C R or 6 C 3. So let's go ahead and do that here. If you want to, you can also press second and enter. And then you can change it right there. So I can put 6 and 3 and you get 20. Cool. So this is telling me there's 20 different ways that I could choose 3 people to fill the commissioner, the city commissioner spot. All right, and that's it for that last prompt. Any question for that last prompt? All right, let's do this next prompt. All right, so for this one, it says, suppose you find 7 articles related to the topic of your research paper. In how many ways can you choose 7 articles, well, 5 articles to read? So for this one, for the 7 article, do you think all 7 articles are the same, or do you think they're relatively different? Cool. All right. So we got 2 people who said different. Good. So for this one, do you think that it matters well, for this one, do you think for the 5 article, can you read the same article? Or is it like once you read that article, can we now read it again? Cool. So you can't read it again. So that means repetition is not allowed. So for this one, the order that I read the article, does that matter? Like, does it really have any precedent? Like, if I read article first or second, third, fourth, or fifth, or is it pretty much all the same? Okay, so it had no, so good. So for this one, what's my N? So we say N is 7. That's so weird. All right, give me a minute, my thing is freaking out. All right. So N is 7. What is my R? So I already saw some of you put R is equal to 5. So we're going to do 7 C 5. So 7C5 will be 21. All right, good job. And that's it for that one. So if you look at these problems, they're not relatively hard, but you have to kind of think about the question. You just go like, does the order matter? Does the order not matter? All right. I think this is the last one for permutation. Yeah, this is the last one for permutation. All right. So for this one, said the television show Survivor start with 20 contestants. At the end, the final 3 contestants left get to plead their case to the jury to become the sole survivor. How many ways can they choose the final 3 contestants? Okay, so for this one, can we kind of assume that all 20 contestants are all different from each other? Cool. So for this one, is repetition allowed? Is it possible for the final 3 to be all the same people? Like at the end, can the final 3 be all the one person? Can it be like John, John, and John? Like, no. For this one, does the order matter of the final 3? like, no, for this one, the final three really doesn't matter because pretty much they had to plead their case to be the sole survivor. So it doesn't really matter the order of the final three. Yes, we just want 3 people at the end. So for this one, what would be my N? 20. What would be your R? So this will be 20 C3. So let's go ahead and do this. 20 C3. So we could go second enter. We could do 20. Cool. So you got 11,000, well, not 11,000, sorry, 1140. So you get 1140. So when they start with 20 contestants, pretty much there's 1,140 different ways that you can have a final three using all of those 20 contestants. So if you look at it, there's a lot of different variation that could occur with those final three. All right, and that's it for that one. Any question in regard to this one? All right. So we're gonna leave this for tomorrow because these are kind of combination. Well, we'll put combos. So these are like kind of like pretty much option that you have to do combos on. So we'll leave this for tomorrow. So just know pretty much anything that we went over today could be on the quiz. So if you kind of notice what we went over a lot conditional probability. We went over the multiplication rule for conditional, the multiplication rule for dependent data set. And we did go over counting technique, the combination and permutation. So for the quiz tomorrow, the quiz is gonna have 5 questions. And I'm gonna show you where to find said quiz. So if you wanna find the quiz, you go over here to the home setting. So this one should be week number 4. So if you go over here, week number 4, that's where you'll find quiz number 5. So just remember for this one, you're gonna have all the way from 7 a.m. all the way to 7 p.m. to take that quiz. So make sure that you take it somewhere in between that time period. And for the quiz, like if you know the material, it shouldn't take you that long to do it. Because if you kind of look at all of the math work that we did today, like everything was pretty straightforward. Like all you have to do is multiply and then you get the decimal value. And just know for all the probability, I want all the probability to be in decimal form. None of the questions are going to ask you for percent. So just always put it as a decimal form. All right. Any question before I close down this Zoom session? Cool. All right, so that's it for today. So just remember for tomorrow, you have your 5th quiz. So if you look at it right now, we're halfway done and we already have 5 quizzes. So it looks like we might have 10 quizzes. So most likely you're gonna drop 2 quizzes. So if you did bad on one of the quizzes so far, just know that we're most likely gonna be dropping 2 quizzes. So that's good news for you. All right, so I'm gonna close this down and I'll post up the Zoom meeting and I'll also post up the lecture notes. All right, so that's it for today. Have a good night. I'll see you tomorrow.